Hi and hello. So today's lesson is going to be about graphing cubic functions. Now, just like we've done in the past, we're going to start with a function, or we're going to start with the parent function, and then begin to analyze it, and then graphing it using transformations. So we've studied quadratic functions. These are polynomials with degree 2. That was our last unit. This unit is going to be about other polynomials. So we'll start with a cubic. This is x cubed. We're just going to take a number, multiply it by itself 3 times. I've got some smallish numbers, relatively easy to find. So when we plug in x, we'll just take it to the third power. Negative 2 times negative 2 times negative 2 is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So now that we have a couple of points, let's plot them and see what shape we get. 0, 0, 1, 1, and then 2, 8. We can see as we go to the right, it's going to shoot off pretty quickly. And as we go to the left, it's going to shoot down pretty quickly. So it kind of looks like a parabola if you just wrenched that left side down. Let's try to draw it so it actually goes through all 3 points. There we go. All right, so now let's look at some of the attributes of our parent function. Domain and range, that's how far left and right, how far up and down the function goes. So the domain is all real numbers, which again, we can write as negative infinity to infinity. Range is how far up and down the function goes. We can see it starts to race up and down pretty quickly. Our range is also all real numbers. End behavior, that's our statement what happens really far at each end. As this function goes to the right, as x goes to infinity, it also goes up. Y also goes to infinity. As this function goes to the left, as x goes to negative infinity, it also shoots downwards. Y goes to negative infinity. So this goes right and up, left and down. Next up, we want to find where it's 0, where it's positive, where it's negative. Zeros are where it crosses the x-axis. This function has exactly 1, 0, and it's at x equals 0. Now, to the right of that, it's positive. To the right of that, it's above the x-axis. So it's positive from 0 to infinity. And then it's negative to the left of 0, 0. So it's negative, or from negative infinity to 0. Right? And a very important distinction from positive negative is increasing and decreasing. Remember, increasing is talking about where is it going up from left to right. And this function is always increasing. So it's increasing on all real numbers, which means that it's never decreasing. Right, so now that we have the parent function down, let's graph a couple of other examples. So as we graph those, we're going to start with our parent function, and then we're going to identify our transformations. So here we've got 3 extra numbers in our cubic function. We've got that 2, which is a vertical stretch by 2. Right? It's outside the parentheses, so it has to be vertical. So we're making the function twice as tall. The first minus 1 is a translation to the right one, right? It's inside the parentheses, so it has to be left and right. And that last minus 1 is vertically translating. It's going down 1 unit. So now that we've identified all our transformations, let's perform them one at a time. So I always start with stretches and compression, so I'm going to multiply all my y coordinates by 2. Negative 8 goes to negative 16, negative 1 to 2, 0 to 0, 2 to 1 to 2, and 8 to 16, and the x coordinates are unchanged. Now if I want to translate right, I have to add 1 to my x coordinate. If I want to translate down 1, I have to subtract 1 from my y coordinate. So I'll just take each point and I'll add 1, subtract 1. So add 1 to negative 2 is negative 1, subtract 1 from negative 16 is negative 17. And I'm just going to go down the line. 0, negative 3, 1, negative 1, 2, 1, and 315. Now that we've found all our points, let's plot them and make sure it kind of looks like what we described. So here's our parent function already ready to go. Let's put our new function next to it. So some of those points don't really fit, so we'll start with 0, -3, and then 1, -1, 2, 1. And it's not going to make a line, so we need to be careful here to make sure we get that S curve going on. And one thing you might notice is that it's 2 units right here from our vertex up to the next one over. As whenever you're looking at a graph, that number, that 2 units, that'll tell you your vertical stretch. So we can see here that it's a vertical stretch by 2 just by looking at that point. All right, so let's check out another example. This time, now that we still have that 2, but it's inside the parentheses, it's happening inside the cubed, that means it's a horizontal stretch or compression. And because everything inside the parentheses happens the opposite of what you might expect, it's a horizontal compression. Instead of being twice as wide, it's half as wide. Now that +3 is a translation left 3 units, and that +4 is a translation up 4 units. And we'll go through and do the exact same thing we did last time. We'll perform our stretches and compressions first. So we'll divide all our x coordinates by 2. So -1, -1/2, 0, 1/2, and 1. And the y coordinates are unchanged by this horizontal compression. And then if I want to go left 3, I have to subtract 3 from my x. If I want to go up 4, I have to add 4 to y. So I'm going to take each point and I'll subtract 3, add 4. So -4, -4. I'll subtract 3 and I'll add 4. So -3.5. 3. And then I'll -3, 4. Right, subtract 3, add 4. So -2.5, 5. Subtract 3, add 4, so -2, 12. And then I'll plot all the points I can. So I can actually fit 4 points on this plot. So I'll start with -4, -4, -3.5, 3, -3.5, 3, -3, 4, -2.5, 5. And then we'll give it its distinct S-bend. And there we go. So just like we can identify a vertical stretch by looking at how far up and down to the next point, if we also check how far left and right, it's supposed to be 1. Since this is only a half, that tells us our horizontal stretch or compression rate there. So that's just a bit of advice if you're ever trying to read a graph, which, spoiler alert, that's our next problem. We want to write the graph based on this transformation. So let's identify what's going on. Our vertex has shifted from 0, 0 to 2, 1. So it looks like it's been translated right 2 units and up 1. And then we need to be able to read our stretch and compression to get from our center point to the next. It's actually up 3. That tells us it's been vertically stretched by a factor of 3. Ignore what I've written. That's supposed to be a 3. 3x minus 2 cubed plus 1. All right, let's check one more together. So this one, if we check out how far it's been translated left 4 and up 1. And then we can also tell that it's been shrunk horizontally. So let's write our left 4 up 1, As we come back to the graph, we can see that it's not as wide as it used to be. That space there, that's only a half a unit. So it's been horizontally compressed by a half. All right, so now we just got to put all of the pieces together in writing the function. The horizontal compression is going to go inside the parentheses, so 2x plus 4 cubed plus 1. That gives us our horizontally compressed by 2, our left 4, and our up 1. All right, now let's one last thing we'll do together, and that's an application. So we have this thing called the square cube law. And to demonstrate how that works, I've got these two cubes. So I've got one that's 2 inches by 2 inches by 2 inches by 2 inches, and one that I doubled the side length, so it's 4 inches by 4 inches by 4 inches. Let's find the area and the volume of each. So each face on the small cube has an area of 4 square inches, right? Because it's 2 by 2, and the cube itself has a volume of 8 inches cubed to 2 by 2 by 2. Let's check it with the 4 and see how it compares. So the area is it's a 4 by 4 on each face, so it's 16. So rather than being doubled, the area was actually multiplied by 4. Let's check what happens with the volume. So our cube is a 4 by 4 by 4 cube. So 4 times 4 times 4 is 64 cubic inches. So rather than being twice the volume or 4 times the volume, it's actually 8 times the volume. This is the square cube law. It says as we double the side length, area is proportional to our scale factor squared, and volume is proportional to scale factor cubed. Right? As you make something bigger, its insides grow a lot faster than its outsides. That's kind of the reason why smaller animals like mice can sustain falls much higher, relatively speaking, than we can. We weigh a lot compared to our area, so we take a lot more force. Now, this is very bad news for someone like Ant-Man as he grows, right? As he gets bigger, his insides get bigger. He gets a lot more weight a lot faster than he gets area. So this will affect how fast or how strong our bones are, right? The human femur is the strongest bone in our body. It's capable of supporting up to 6,000 pounds. But Ant-Man's weight is gonna grow fast. So I want to figure out how many times bigger can he get before his femur, the strongest bone, will give out. So I checked on the internet, and the average adult male is 196 pounds. So that means we should have an equation that looks something like 196 times x cubed. So let's see what happens. If Ant-Man doesn't change his size, right? He's just 1 times his original size. It makes sense that his weight would still be 196 pounds. So I'll plot that point 196. We'll have to do some estimation, right? That first line is already at 2,000. If he makes himself 0 times the size, it makes sense that he'd weigh 0 pounds. And the rest of the points is where it starts to get a little interesting. If Ant-Man makes himself half the size in each dimension, he will actually weigh 1/8 of his weight. He'd be 24 pounds or so. If he makes himself twice the size in each dimension, twice as tall, twice as wide, twice as deep, he'll weigh 8 times as much. He'll weigh 1,568 pounds, roughly. If he makes himself 3 times the size, that means he's actually going to be 27 times the weight. 3 times 3 times 3. Which means he'll have a weight of around 5,292 pounds. Now this is pretty close to our to the ultimate strength of our femur, but let's go one more step just to see what happens. If he makes himself 4 times his size, that means he's going to be 64 times as massive, 64 times as heavy, which means he'll have a weight of 12,544 pounds. So we get this kind of curve representing his weight over time. And remember, we're looking for where's he 6,000 pounds. We can solve any equation we want by graphing, as long as we put a horizontal line where we're looking for it equal to. So we can see that is right around 3. If I check with Desmos, it's about 3.2. So Ant-Man can get about 3.2 times his size before his femur, his strongest bone, gives out. Thanks for watching. Please let me know if you have any questions that I can answer.